Okay, okay, then I will start my talk. Okay, thank you again for the introduction, and it's for the opportunity to speak. So I want to discuss some of my recent work on diagonal cycles and triple product of functions using the method of Bertini-Damon involving level raising of modular forms. So, so I want to first introduce the setup. So I would denote this, I'm given a triple of modular forms, which I will call triple F. There are new forms of level n of way 2, and I will assume that n can be factored into n plus and n minus, with n minus being square free. And then I will say that we're in the definite case if n minus consists of odd number of prime factors. And we'll say we're in the indefinite case if n minus consists of even number of prime factors. This terminology comes from the fact that in the definite case, we'll use Jacques-Ellul transfer to transfer these modular forms to modular forms on definite quaternion algebras. And in the indefinite case, we'll transfer these modular forms to modular forms on some indefinite quaternion algebra. Okay. And in the definite case, we'll assume that the global root number of certain triple product function is +1, and moreover, the
sorry,
triple product.
Haining, do you think you can make the slides bigger? It seems like your slides are squeezed.
Yeah, but is this okay?
Yeah, if you go to the next slide, can we see what it looks like? Yeah, that's much better. Thank you.
Is it? Okay.
Yeah.
That's much better.
Yeah, that's perfect.
Okay, but I guess I'm hiding away part of the slides, I think. But we'll see. Okay, sorry. I'm quite inexperienced in giving a Zoom talk. So in the indefinite case, we'll assume that the global root number is -1, and we'll assume that the Gross-Schoen diagonal cycle class is non-zero in the Selmer group. Okay. But this, how do I?
So Patrick suggests that you use slideshow rather than full screen. Can you try that?
Yeah, but I think the problem with slideshow is that it automatically turn the page, I think, instead of is this okay?
It looks good to me.
Okay, but I think the problem is slideshow. It automatically.
You can click the pause button at the bottom, can't you?
The pause button.
In the slideshow mode, there's 3 buttons at the bottom.
Okay, sorry. So as I said, okay, so next I want to introduce the triple product of function. So first of all, this triple product function is defined by by the product of Euler factors for when the real part of S is greater than 5/2. So I will not discuss anything about the Euler factors when these at primes dividing this n, but I'll only simply tell you what the Euler factor looks like when this p doesn't divide n. We'll call these the good Euler factors. So
sorry, Okay, I have a
yeah.
question about the last slide. You said the L function is not 0 and epsilon is +1. Do you mean the L
No.
function is 0?
I will assume that the assume when the epsilon the root number is +1, the L function doesn't vanish.
Doesn't vanish. Okay.
Yeah, and assume that when the root number is -1, then the Gross-Schoen diagonal cycle is non-zero. This is a replacement for the condition of the derivative of the L function is non-vanishing.
I see. I see. Thank you. Thank you.
Is there some natural condition, like if you assume all of the FIs are like mu at this level or something, is the global root number,
Yeah, so
it just is that, right? Or is that
so
not?
if I assume n minus, assume n is square free, and we're in a definite case, and suppose these modular forms come from elliptic curves and they all have splitting multiplicative reduction, then this is equivalent. Then the definite case is equivalent to the root number is +1.
I see. Okay, thank you.
Okay, so suppose the Q expansion of the modular form is given by this, and then at p not dividing n, which is a good prime, then suppose the Hacker polynomial is factors as x minus alpha I times x minus beta I. So the alpha I and beta i's are the eigenvalue, the roots of the Hacker polynomial, and then the Euler factor at p is given by this degree A term, where you just choose either alpha or beta for these for the coefficient in front of p to the negative s. This triple product function has a functional equation relating the value of the triple product function at s to 4 minus s. So the center is given by s equal to 2. Okay. So we'll denote by I will make a very simplified assumption that the modular forms in triple F are defined over the same Hacker field. This is just for simplicity, and it's not necessary. And if it's not, then you can just work with certain triple tensor product of Hacker field instead of one Hacker field. And suppose lambda is some place over L for this common Hacker field, and I complete this Hacker field at this place lambda, and I call this the L-adic Hacker field for this triple F. And O will be the evaluation ring of E lambda, and we'll write O sub n to be O modular pi to the, pi is some uniformizer in O, and On will be O modular pi to the n, and F lambda will be the residual field. Okay, so to each modular form Fi, you have a Galois representation attached to it, characterized by the fact that the Frobenius, the trace of Frobenius correspond to the Fourier coefficient at good primes. And I'll use this notation V triple F to denote the triple tensor product of these three Galois representations. Okay, and then I will fix a TI stable. I would fix a Galois stable lattice instead of this Galois representation, and I will denote it by TI sub n to be this lattice modular pi to the n. And then I have this finite Galois module, which is just the triple tensor product of TI n. Okay. Okay. Now I want to define this Bloch-Kato-Selmer group. So first, I recall that the finite part of the Galois cohomology is defined. The finite part of the Galois cohomology of so V is a finite place of Q and the finite part of Galois cohomology of QV valued in this V triple F is defined to be the Galois cohomology of the residue field at V valued in V triple F with inertia fixed by the inertia. So IV here is the inertia. So in this talk, we'll not concentrate on this V triple F itself, but I will twist it by -1. This will become clear later why I want to do that. But for now, you only need to know the fact that it's when I twist it by -1, this becomes self-Kummer-Due. And then I want to define this Bloch-Kato local finite part. Yeah, I want to define this finite part at L. The definition is due to Bloch-Kato. This is by definition of the kernel of the Galois cohomology of QL valued in V triple F mapped to H1 of QL V triple F tensor with the B Chris. Okay. Why I'm getting stuck again? Okay. Then I would define the Bloch-Kato Selmer group to be the subspace of classes of the global Galois cohomology of Q, such that locally at L, this class should lie in the Bloch-Kato finite part, and at places not dividing N, this S should lie in the finite part, defined as above. Okay. So the motivating conjecture of this work is the following. And this is, I will refer to this as the rank 0 case of the Bloch-Kato conjecture for the triple tensor product motif. So if we assume the central critical value of the triple tensor product function at 2 is non-zero, then we expect that the Bloch-Kato Selmer group should vanish. Actually, I cannot quite prove this conjecture in this generality, and I will discuss why. But I can prove a special case or a related case. This is the case when sort of this triple F degenerates, namely the triple F consists of a single modular form F. And in this case, if you look at the triple tensor product Galois representation, this factored into the symmetric cube component, and then and the direct sum of the Galois representation of F itself twist by 1. So if you twist this by -1, then the symmetric cube component pick up this -1, and then the other two factors are just the Galois representation of F itself. And in accordance to this factorization on the Galois representation, you also have a factorization on the triple product tensor L function, triple tensor product L function, that factored into the symmetric cube L function for F, and the L function for F itself. You actually have two copies of the L functions for itself. So I briefly remind you the symmetric cube L function is at a good prime, the Euler factor of the symmetric cube L function for good prime is given by this degree 4 term, where alpha and beta are again the roots of the Hacker polynomial for F. Okay, so what I can prove is the following theorem. Suppose the modular forms satisfy these 4 quite technical conditions. First of all, I asked the residual Galois representation of this modular form is irreducible. So I exclude sort of Eisenstein is from, or exclude Eisenstein theories. And second of all, I assume that this space of quaternion ionic modular forms on some definite quaternion algebra localized at the maximal ideal corresponding to this F is free of rank 1. This is a quite technical condition. I won't spend too much time on this, but what this really means is that I want to kill the congruence module for this modular form. And this condition is referred to as the p-isolated condition in literature. And this, yeah, so let me just say that I want to get rid of the congruence module for F. And the third condition is that this residual Galois representation has large image. I simply assume it's surjective. And the fourth assumption is that I assume, because of this factorization, I want to assume that the L function for F itself is non-vanishing. And so therefore the non-vanishing of the triple product function is equivalent to the non-vanishing of the symmetric cube L function. Okay. And then under these assumptions, if the symmetric cube L function for F is non-zero, then I can prove the Bloch-Kato Selmer group is 0. Okay, so this is sort of the rank 0 case for the symmetric cube motive of the modular form. The rank 0 case of that. Okay. Yeah, so I want to give a full sketch of the proof of this theorem. First of all, I want to relate. So the L function is something that's defined anyway, and I want to pin down its sort of the algebraic part of it, and by a general philosophy of Gann-Gross-Persar, these are usually related to some pure integral, and I won't tell you which pure integral it is. So the pure integral in this case are called the Gross-Kudela period. Remember we're in the definite case, and so n minus has all number of prime divisors. This means that there is a definite quaternion algebra with discriminant n minus, and we form this double coset, this double coset is actually finite, and we refer to this double coset as the Shimura set, and which will be denoted by x upper b. Here, this Rn is an actual order of level n plus. Okay, and why we're doing this is that according to our assumption, these modular form Fi can be transferred, can be realized as a function on the Shimura set, which I will denote by this symbol S2b n plus O. And the Jacques-Lalande transfer of Fi will be denoted as Fi upper b. They can be simply viewed as functions on this Shimura set. Okay, and then we can consider the diagonal embedding of this Shimura set in the triple product of Shimura set. The triple tensor product of these FIB and integrate along this this diagonal embedding. And in our case, this is simply, and I would define this as the Gross-Kudela period. It's just simply a finite sum. You simply take the value of FIB restricted to the diagonal, and then and sum it up. Okay, so this is called a Gross-Kudela period, and it's an important theorem of Harris-Kudela, and then refined by Gross-Kudela and Ichino that if the central critical value of this triple product function is non-zero, and then the Gross-Kudela period, this pure integral is non-zero. Okay, so in the symmetric cube case, since I have the assumption that symmetric cube L function is non-zero and the L function is non-zero, the triple tensor product dipole function associated to f is non-zero. So the gross Kudala period in this case is non-zero. Somehow, so by this theorem, I can rephrase the conditions in my theorem as saying that the gross Kudala period is non-zero. And as you have seen that it's the gross Kudala period is the finite sum of algebraic values, and it's more you can relate it to geometric quantities easily. Okay. So next I want to, okay, I just want to check. Next I want to review a little bit about Tate local dualities. So if P is a prime and F is a p-adic field with residue field K, and then if is a finite Galois module over On, which I assume is self-Krummer due. This means that here this due means it's Pontryagin due. This self-Krummer due means that M is isomorphic. Sorry, this is isomorphism to the Pontryagin due of M twisted by 1. And then we can define the finite part as similarly as defined before, and the singular quotient of the Galois cohomology of F valued in M by the quotient of the Galois cohomology by the finite part, by its finite part. And then the finite part inflates into the Galois cohomology of F, and by inflation restriction exact sequence, the singular part is it can be computed as this. Here IP is the inertial group of F. Yeah, and the G sub K is the Galois group of the residual field. And I will write the natural quotient map by partial P and refer to this as singular quotient map. Then you have the local Tate pairing for the Galois cohomology of F. This is a perfect pairing, and the finite part are isotropic inside of under this pairing, and this means that the finite part and the singular part are due, and the singular quotient are due to each other. Okay. So this is sort of the local Tate dualities I need. Okay, now I want to introduce actually two crucial ingredients for the proof. So more notations first. So if F is an eigenform, then I will denote by phi sub F the morphism from the Heck algebra to O. So here T is certain Heck algebra I will not introduce formally. So this is the Heck algebra sort of acting on the new part of on the space of modular form way2 of level n, which are new at n minus. And this morphism it just corresponds to the Heck eigensystem of F. It's in the Heck algebra at P to the P's Fourier coefficient for P not dividing n, of course. Then I can also look at the Heck eigensystem modular pi n. So I take this morphism and reduce modular pi n. I have this modular pi n version, which I will denote by phi fn. And I will write IFN as the kernel of this morphism. This is just a notation. Okay. Then the first crucial ingredient is that I want to find a special prime, which I will tell you exactly what it is, such that the singular quotient of the Galois cohomology at P, valued in the symmetric cube component, is isomorphic to the triple tensor product of the space of quaternionic modular forms modular this ideal IFN. And this geometric relation between the space of modular forms and the Galois cohomology is will be referred to as the ramified level raising. Here you see that Yeah, I will explain why this is called ramified level raising in a minute. The second crucial ingredient is I want to construct some global Galois cohomology class kappa for the symmetric cube component, such that the singular residue of kappa, when paired with a sort of generator of this space, is equal to this Gross-Schoen period, at least up to some units. So here, this pairing is is a certain natural pairing on the space of quaternionic modular forms, or rather, it's the pairing on the triple tensor product of the space of quaternionic modular forms. I want to construct this kappa in a way that it almost lives in the Selmer group, but not quite. The difference between this kappa and an element in the Selmer group is only different at P. P is this special prime. And the reason I want to do that is that, recalling the Selmer group, the local conditions at such P are at the good primes are given by this finite condition, and the finite by the finite part, and the finite part is the isotropic under the Tate duality. And what I will do is I will pair this kappa with some element in the Selmer some element in the Selmer group, and write this as a sum of local Tate pairings. And because of this property, I can see that many many local terms are vanishing, and there's only the only interesting term left is the local pairing between kappa and any Selmer class at P. And sort of you will see this in a moment why I want to do that. Okay, now suppose, yeah, I will tell you how exactly I can construct this kappa, but for the moment I assume this kappa is constructed, and I want to finish the proof for the Bloch-Kato conjecture for the symmetric cube case for the symmetric cube motive in the rank 0 case. So recall that our assumption is that the Gross-Schoen period for F is non-vanishing. We want to conclude that the Selmer group is actually 0. So we'll work with this finite version of the Selmer group, and we'll prove by contradiction, and we assume that this finite Selmer group has rank greater than or equal to 1. We want to conclude a contradiction so that it actually has rank 0. And in this case, we can, in fact, find a generator we can find a free rank 1 submodule in this finite Selmer group, which has generator C. And I will do exactly what I explained before. I want to pair this kappa, this conjectural kappa, with C under local Tate duality, and I want to sum this over all the places over Q. And since the global invariant for the Brouwer group is 0, so by global class field theory, this global this sum is actually 0. And the property that kappa almost live inside of the Selmer group except P implies that, as I explained, this local term is 0 for almost all the places except this one at P. This is lying a little bit because I did not define the local conditions at places dividing n. This is of course not true for those places, but this issue is not very serious and it can be easily handled. So I will just pretend here that the kappa has this property. Since the sum is equal to 0 and all the local terms are 0 except at P, the local term at P has to be 0. And since kappa, since the finite part at P is isotropic in the local Tate duality, you can quotient it out, and the only thing matters is the singular part of kappa. This means, I think C is a generator, and we can choose it to have a non-vanishing finite part. We can conclude that the singular part of kappa is actually vanishing from this equality. But this is a contradiction because by the sort of the third crucial ingredient, or I forget to, which I forget to call the reciprocity law. By the reciprocity law that tells you that the singular part of this kappa is related to the Gross-Schoen period, which by assumption is non-vanishing. So this singular quotient cannot vanish, and this is a contradiction, and the theorem is proved. So the strategy is rather simple. You simply just pair this kappa with anything in the Selmer group, and using this property to conclude that kappa is an annihilator that kills anything in the Selmer group. And because of this non-vanishing of Gross-Schoen period. Okay. Next I want to, next I want to tell you what kind of special prime I'm looking for. These primes are related to level raising congruence between modular forms, and they're usually called the M-admissible prime for F. So these are defined by those primes such that they're good primes. They don't divide N and L, and also that L does not divide p squared minus 1, and thirdly, pi to the n divide p plus 1 minus certain number epsilon times the Fourier coefficient of f at p. These epsilons are valued in -1 and +1. So the way to think about this is that the third condition, pi to the n, dividing p plus 1 minus epsilon p times APF, is sort of equivalent to the fact that locally at p, this modular form, I mean the automorphic representation, the automorphic representation locally at p for this modular form look like a Sternberg representation. And this condition L not dividing p squared minus 1 is sort of saying that the Frobenius eigenvalues of the Galois representation at p, when restricted to GQ p squared, are distinct. They're not equal to 1. There are two eigenvalues. Okay, and this sort of put you in the position of the case where this sort of Mazur's principle applies. So it's known by work of Ribet that these p's are exactly those level raising primes for f. What this means is that you can find a congruence between a new form of level pn, which I would call f p raised, such that it's congruent to f modulo pi to the n. In this case, the third condition here tells you that the Frobenius acting on this Galois representation with eigenvalues epsilon pf and epsilon pf times p. So the two Frobenius eigenvalues are for this mod pi n Galois representations are epsilon pf and epsilon pf times p, and by the second condition, they're distinct. Okay. So now I'm going to introduce a proper extension of this notion to the triple product situation. I will call this the n-admissible prime for f triple. What this is I simply ask p to be an n-admissible prime for each of the modular forms in f triple. So these are the first three conditions. And the fourth condition is something new, and it's important. So I ask the epsilon appearing in the third condition to multiply the product of these epsilons multiplied to 1. This condition is responsible for two things. First of all, you want sort of the local root number of the triple tensor product of function to change at this p. When you level raise this this triple of modular forms, and this is exactly the condition that the fourth condition needs to happen. Okay, so the first reason I want to introduce this condition is that I want to change the sign locally at p for the triple tensor product function. The second reason is I'm working geometrically with Shimura curves, and the Shimura curve has certain nice properties when you base change to qp squared instead of qp, and I'm going to working with integral models of Shimura curves over zp squared, and then but since I'm studying Summer groups over q, I need to eventually descend this to qp, and this condition guarantees that. And it has something to do with the asking linear involutions on acting on these Shimura curves, which I don't have time to say much. Okay. Some more notations. So I will denote triple of these ideals given by the sort of mod pi Hacker eigensystem by using this notation. And then we have the level raised version. And then we collect the triple of ideals given by the Hacker eigensystem of the level raised modular form. Then we have the mod pi n Galois representation for each of the modular form, and we have the level raised version. Since the modular forms are congruent to itself, and the level raised version will be isomorphic to down level raised version. So these are just some notations. Next, I want to find a space that I can realize these level raised Galois representations. Recall that the level raised modular forms are new at P, and by Jacques-Lalland's correspondence, they are realized on quaternion algebras that are ramified at P. So, what I have to do is I have to take this quaternion algebra and add P to its discriminant. And but since you cannot change one invariant for quaternion algebra to get another quaternion algebra, you also have to find another place and change the invariant. And when you switch the invariant, you get an indefinite quaternion algebra of discriminant Pn minus. And this level raised Galois representation will be realized on the Shimura curve associated to this indefinite quaternion algebra, which I will denote by x prime. What this means is that the first Galois cohomology, the first cohomology group of this Shimura curve modular this ideal IP raised will be isomorphic to this Galois representation corresponding to the P raised modular form. So here I twist the cohomology group by 1 so that this matches the Tate module of the Jacobian of this Shimura curve. This twist is important and explains why I twist the triple tensor product by -1. Okay. Now I look at the triple tensor product. Since I'm going to study the triple tensor product Summer group, it's natural to consider the triple product of these Shimura curves, and I take the middle degree cohomology of the Shimura curve twist by 2. And I modular this triple of ideals. And then by Cunis formula, only the only term surviving this middle degree cohomology is the H1 term. This is because this ideal is non-Eisenstein. This ideal I is non-Eisenstein, and the term H0 and H2 are Eisenstein are Eisenstein Hacker modules. So when you modulate this ideal, the only term survive is the H1 term. And since I twist by 2 here, I have to twist by -1 so that this matches the twist. And since this cohomology realized this level raised Galois representation, this middle degree cohomology of the threefold gives you the triple tensor product of the Galois representation. Okay. And then I have the cycle class map from the Chow group of codimension 2 to the degree 4 cohomology of the Shimura curve over Q. But as I explained here, again by Q-ness decomposition, the only term can survive are sorry. This Q should be Q bar, and kind of mess up here. Again, by what I explained here, the house chart cell spectral sequence tells you that this H4 term of the Shimura curve is actually is isomorphic to the H1 of the Galois cohomology of Q valued in this middle degree Galois cohomology of this threefold. And then here, the isomorphism explained above tells you we have this isomorphism from the cycle class map actually mapped to the Galois cohomology of Q valued in this triple tensor product of Galois representations for this triple F. Here, using the fact that the level raised Galois representation is isomorphic to the on-level raised Galois representation. Okay, so this is the Abel-Jacobi map. And a natural class in the Chow group here is the so-called Gross-Schoen diagonal cycle. We simply take the Shimura curve and diagonally embed it into 3 copies of them. And the kappa I'm looking for will just be the Abel-Jacobi map of this diagonal class. Okay, and this Shimura curve at P admits the so-called Schragnick-Dringfeld uniformization. What this means is that the formal scheme associated to the special the formal completion of this integral model of the Shimura curve at the special fiber admits a double coset uniformization. Here, this M is the Dringfeld upper half place. Yeah, and I just remind you that XB is the Shimura set appeared before, and XB not P is the Shimura set when you add a level structure, add a gamma not P level structure to your original Shimura set. This is defined by some Eckler order of level Pm plus. This Dringfeld uniformization gives you a convenient way to describe the special fiber of this Shimura curve. So by the way, this Shimura curve, the reason I want to level raise this to VP squared is this becomes a Mumford curve over VP squared. And I won't explain what Mumford curve means, but here is the description of this special fiber. The special fiber is a union of 2 P1 bundles over Shimura set. Which are denoted by XB plus and XB minus. These Shimura sets are both isomorphic to the Shimura set I introduced before as XB upper B. What this means is all irreducible components are P1 bundles. P1 are P1s, and they are parameterized by by 2 copies of the Shimura set. And the P1s on each over each of the bundles over each of the Shimura set will not intersect, but P1s over different Shimura set will intersect at the ordinary double point, and the total intersecting point is parameterized by this Shimura set with level with the gamma not P level added to it. And this also agree with the singular points on the Shimura curve. Okay. Looks like I probably cannot finish on time. Yeah, I will now I want to introduce the narrow model of the the Jacobian of the Shimura curve, and that will denote the sort of the graph of reduction graph of the narrow model, the special fiber of the narrow model. This is a semi-abelian scheme, and the vertices of the reduction graph is by the previous theorem is simply given by 2 copies of the Shimura set, and the edges of the dual reduction graph is given by sort of singular points, and it's given by this Shimura set, adding a level gamma naught p to it. And then I will introduce the character group of the Shimura curve at P by the kernel of sort of the edge, the map, the target and source map from the module, the vertices to, sorry, the edges to the vertices, and I will define the co-character group by the sort of the dual of this of the character group. So I won't need this. I really don't need the definition of this D lower star and the upper star, since I'm giving you a very concrete description of the edge set and vertex set, and you will see what exactly these are in a moment. And then I define the component group to be the co-character group modular the image of the character group in the so-called monodromy pairing. So the way to think about the character group is, since the edge set is given sort of by the space of quaternionic modular forms of level Pn plus, and there is 2 natural degeneracy map from this space of modular forms to the space of modular form without P in it. And the character group can be think of sort of as the kernel of this, the sum of the natural degeneracy map. So you can think of the character group as the sort of P nu sub module of this space of modular form, quaternionic modular forms. And the co-character group is sort of the dual version of it. So you can, so instead of the kernel, you have the co-kernel here. And it's the P nu quotient of the space of quaternionic modular forms of level Pn plus. Okay. So they're kind of isomorphic to each other because they are corresponding to new forms at P. So the component group is defined as the co-kernel of the map obtained by composing D upper star and D lower star, which is a map from the vertices to vertices. And since I identify these with degeneracy maps from the Shimura set, this is given by some matrix, 2x2 matrix, and this matrix appeared everywhere in the literature for modular forms. It's simply given by the TPs on the diagonal and the P+1, negative P+1 on the anti-diagonal. Okay. Why this is interesting is because recall that P is an inadmissible prime, and if you compute the determinant of this this matrix, you have AP squared minus P+1, and this corresponds to the definition in the definition of n-admissible prime, the second condition in the definition of n-admissible prime, this tells you that this matrix actually degenerates, and since the component group is this co-kernel, only 1 copies of this space of quaternionic modular forms left when you quotient out this by this ideal. And also it turns out, since the Galois representation is unramified at P, sort of the monodromy should vanish, and therefore the monodromy pairing should be completely degenerate, and the co-character group is actually isomorphic to this component group. You can also sort of think of this as the P nu a space of p nuiforms in the quaternion ionic modular forms, and this is the sort of the p old forms. And this is sort of saying that there is a unique lift from the p old forms to the p new forms. And as a matter of fact, these the character groups and the co-character groups are both isomorphic to the component group. Okay, so the Jacobian of the Shimura curve is the Shimura curve itself is a Mumford curve. So the Jacobian of the Shimura curve has purely toric reductions. And what this means is that there is a rigid analytic uniformization of this form. If you have not seen this, you can think about the Tate curve, and in that case, chi p is just z, and chi p2 is also z, and this recovers the Tate uniformization of gm modular q to the z. And it also should be familiar to you that once you have this rigid analytic uniformization, the cohomology of the Shimura curve, or rather, which is equal to the Tate module of the Jacobian, can be sits inside of this exact sequence. This should remind you of the familiar fact that for the Tate curve, this is QP twist by 1, this is QP. And since the thing in the middle is the representation for the p raised modular form. It's exactly the Galois representation for the p raised modular form, which is isomorphic to downraised Galois representation for the unraised modular form. In particular, it's unramified. So this exact sequence actually splits, and you just have, and I will call the co-character group by F plus and the character group by F minus. And what this does is it allows you to compute the singular quotient of the triple tensor product Galois representation. And recall the singular quotient of the triple tensor product Galois representation can be computed using the inertial group at P. So you have this isomorphism. Since this triple tensor product Galois representation is unramified, taking H1 is the same as taking the Helm. And this Helm actually factors through the taming inertia. And in fact, the only factor left in the taming inertia is the factor at P squared. Oh, sorry, this is L. Sorry, this is ZL. Because this is the L-adic representation, so this is ZL. So the only factor in the taming inertia that left is the factor at L, and you have a Helm L to this triple product Galois representation. And remember, this is twist by -1, and you can move this to here, and you have this Helm. So the singular quotient is equal to the Helm of ZL twist by 2 to the triple tensor product of Galois representations. Since this triple tensor product Galois representation is realized as the middle degree cohomology of the triple tensor product of Shimura curves, this allows you to compute this space. This 2 means that in the triple tensor product, 2 of the factors should come from F plus, because this F plus corresponds to twist by 1. So 2 of them should come from F plus, and exactly 1 of them should come from F minus. And therefore, we have this isomorphism from this space to this direct sum of 3 copies of triple tensor product. And since F plus is isomorphic to the co-character group, and F minus is isomorphic to the character group, which are both isomorphic to the component group, you have this isomorphism from singular quotient to the to 3 copies of triple tensor product of the component group. And by the degeneracy of the matrix A, you can lower the level to this quaternion ionic space of modular forms, because the component group is isomorphic to one copies of this quaternionic space of quaternionic modulus forms modulo this ideal I. So the conclusion is that the singular quotient is isomorphic to 3 copies of these spaces. And it turns out you do the computation for the symmetric cube component, only 1 copy left. And this is sort of the reason why my method works for the symmetric cube case and not work in the triple tensor product case, because sort of for the Euler system argument to work, you need sort of the singular quotient to be of rank 1. And this is only the case for the symmetric cube component. As I explained, the condition for the product of epsilon multiplied to 1 allows you to descend this over QP. And you can then you can take this kappa and take a singular quotient. And since we have this isomorphism, we can realize this singular quotient as a element in 3 copies of quaternionic triple tensor product of quaternionic modular forms. And I will denote by this upper J to be the projection to the J's copy of space of quaternionic modular forms. Since this kappa, remember this kappa is given by the diagonal embedding of the Shimura curve to the 3 copies of the Shimura curve. It's not hard to imagine that when you pass to the component group, this partial P upper J is up to a unit given by this diagonal embedding of the component group to 3 copies of the component group, which gives you the characteristic function of the Shimura set into the 3 copies of the Shimura set. And then you plug in this definition into the pairing I discussed. You pair this characteristic function of the diagonal embedding with a generator sort of 1 copy of the space of quaternionic modular forms, you will see the Gross-Schoen period. And this finished the proof of the reciprocity law. This allows you to relate the singular quotient of kappa to the Gross-Schoen period. And if you are in the degenerate case, then this is exactly the third crucial ingredient in the sketch of the proof, that the singular quotient, you can ignore this J here, and the singular quotient of kappa is exactly equal to the Gross-Schoen period. And if you sum up all the, let's see, oh, this is the rank 1 case. Yes, this is all I need to prove the rank 0 case. And I think I will stop here.
So are there any questions for the speaker?
I have a question. Can you hear me? Hello?
Yes.
Yeah, I can hear. Yeah.
Okay, Haining, yes. So there are 2 parts in your proof, right? There's a part which is general, and that applies to a general triple tensor product, right, of 3 modular forms, namely your reciprocity law.
Yes.
And then there's the part where you have to specialize to the symmetric cube to get a result about in this rank 0 case. And the symmetric cube, of course, what you're using is you're exploiting the fact that the underlying motive, which is of rank 8, decomposes into a number of components, and then you get lucky because your local target for the singular quotient is 1-dimensional.
Yes.
For the symmetric cube, right? Now, are there any?
Yes.
Are there any other situations of such decompositions of the motive into smaller pieces that you might be able to say something? Like, I'm thinking of the case where maybe some of the F's might be theta series or so. I mean, there's this whole collection of cases where sometimes you can hope for further breakups of the motive.
Yeah, that's certainly interesting. Yeah, actually, Yeah, yeah, it's natural to think of the a single modular form tensored with two theta series, and this decompose. Yeah, I actually never tried this, but it's probably something worth thinking.
Right, I think it's something that actually, I know Kartik Prasanna was interested in this, exactly the case that you mentioned some time ago, and I'm not sure what the status is now of what we know about the arithmetic. If you take a modular form and a higher weight theta series, I think it would be interesting anyway.
Yeah.
I mean, I don't
so,
know.
but I feel the annoying part is that when you apply this method, you always have to assume the factor of the smaller pieces doesn't vanish in order to get your result on the pieces you're interested, which is certainly not a very good assumption, right?
That's something that even comes up in Kato's approach, right? In Kato's results.
Yeah. Or something reminds you of your result with Roger, where you assume certain p-adic function doesn't vanish, and you get the rank 2 case of the Birch-Thorne and Millai conjecture for the elliptic curves, right?
Mm.
Yeah.
Yeah. But I mean, as soon as you have this situation, I mean, what the method really, the diagonal cycle really wants to tell you about the arithmetic of this motive of rank 8, right? And and sometimes you can have control over the arithmetic of a factor, but assuming something about the auxiliary pieces that play a bit of a parasitic role in your study.
Yeah. So I also want to take this opportunity to mention the rank 1 case, and then the situation is really unlucky. So consider this factorization. Now consider the triple tensor product L function has root number -1, okay? And so the parity is odd. And you consider the case where F corresponds to an elliptic curve of square free conductor. And then the root number of F is in fact equal to the root number of the triple product L function. And here you have 2 copies. So this means that the triple product should vanish of order at least 3. And by Gross-Zagier formula, you see that the diagonal cycle can never see anything in the triple product. So in this situation, you cannot even say anything about a symmetric cube. And this is really very unfortunate, I think. Yeah. So this means that if you think about for the elliptic curve, the majority of them has order of vanishing 0, 1, and then the case for this triple product might be different. Maybe there are some case there are quite a big proportion of them just vanishes out of order 3, I think.
Oh.
Yeah.
The triple product, yeah, but it's still degenerate, right? Because you're taking the 3 modular forms to be equal.
Yeah, but I even kind of want to guess that by what I've seen for the level raising method, that even for the general triple product, that might be the case. I don't know if anyone computed this before.
That's interesting, yeah.
Yeah. Because here you do see have this rank 3 singular part, which tells you sort of when you level raise in certain way, the Selmer group become rank 3 instead of rank 0, rank 1. Yeah.
Right. Yeah. And if among your 3 modular forms, if only 2 are equal, then you don't get anything, huh? You don't have any.
Yeah, because it's become rank 2. The singular part become rank 2 instead of rank 1. When you think about it.
The singular part. Yeah, but then you have these 2 pieces, right? So you have, if you have F, G, G, then you have F, and then F tends to the adjoint of G. Up to a list.
Yeah.
And so.
The adjoint, the F tensor adjoint of G has single quotient of rank 4 or rank 2 instead of rank 1. And I think the method still doesn't apply here.
Yeah. Right, because I see, yeah. Because in your setting, you have two factors of
modular form at f.
Right, that you have two f's, and those eat up each one piece of a singular quotient, and then you're left with only one in the piece that you're interested in. Yeah.
In the theta series case, then actually, how would that singular quotient split? Like if you had like f and then two theta series with the same like CM field, say, then the tensor product of those latter two would decompose into like two pieces, right? And then so you would expect the singular quotient, the rank 3 singular quotient, to also decompose into two pieces, wouldn't you?
Yeah, that's true, I think.
But like, would one of them be rank 2 and one of them rank 1 for some reason? I'm struggling to think how that works.
I think you also have to choose very carefully about your theta series. I never tried, but I think that's interesting. Yeah, I don't know actually.
And this question you were raising for the rank 1, the analytic rank 1.
Yeah.
You can't get around it by suppose you have an elliptic curve of odd analytic rank, right?
Yeah.
Kind of a way to kind of try to get around that is to take a twist, or to take a quadratic twist of the curve which has analytic rank 0. But there's nothing you can do of that sort, right? To get because here you know if in this decomposition here of the VF of -1 V boldface of, if you could replace VF by some twists, but I think it doesn't work, right? Because
I think the sign changes occur simultaneously.
You would also twist the triple product.
Twist the triple tensor product.
Tensor product, yeah.
Yeah.
Symmetric cube, I mean, yeah.
Yeah, I think this, I should mention the work of Yifeng Liu here. It's probably the right thing to look for the rank 1 case. What you do is you take an elliptic curve and you base change to a cube extension. And you also have this decomposition into symmetric cube and the twist of f by some cubic character. Then there it's actually expected, as you kind of have already thought about, the cubic twist. You can find some cubic twist such that the modular form, the L function of the modular form doesn't vanish, and then you can say something about the symmetric cube without running into this kind of problem. So yeah, I think that's probably the right approach. But here you don't have any. I think there is no result about the analog of result of Murdy on the quadratic twist of modular form in the cubic twist setting. So
yeah,
something. It's a quite difficult analytic number theory problem. Yeah.
So sorry, just a question. So in this rank 1, if the global root number is -1, you're saying the problem is that you get order vanishing 3?
Yeah, because here the root number for the triple tensor product is equal to the root number of f. Yeah, so you already have 2 copies, and you must have this.
But so then you're worried. You're saying that your diagonal cycle is not telling you anything, right? Because it doesn't go beyond rank 1.
Yeah, because here you have Gross-Schoen formula, and you assume the height pairing is non-degenerate. It doesn't project to the
There's other cycles, right? Like you could consider the Cereza cycle on that is known to sometimes account for higher rank in these settings, in triple product settings.
Oh, I don't know what these cycles are.
Yeah, I mean, you could consider on your abelian variety. Your triple product of abelian varieties, you can take the Cereza cycle, which is basically, well, I mean, anyway, yeah, it's something to think about maybe to play with those. Yeah.
I have a couple of questions.
Yeah, sure.
The first thing is that, so like, you can compute the singular quotient for like a level raised prime of like your representation mod L to the n, where the prime is level raising for exponent L to the n. And that doesn't actually you don't actually make use of a specific level raising of the modular forms, right? Like if there could happen to be many different level raisings when you add p to the level, but it doesn't matter. They because you don't actually pick a specific one. And
so in the situation I'm dealing with, I think there is a unique lift in terms of Hecke eigensystem.
I see. Is that because the L does not divide p squared minus 1 assumption?
It's exactly. And I'm also killing the congruence module, I think, because I assume that the.
I thought that you were assuming L, you're assuming L isolated, so the congruence module down at level n minus is trivial. But couldn't you have a bunch of growth when you go up to level? Oh no, but I guess the growth is understood in terms of this difference.
Yeah.
But even if the congruence module is only you only get a single factor of L, for example, couldn't does that preclude the possibility of having say one level raised modular form which is congruent to the unit stabilization versus one maybe that's congruent to the other stabilization at the other root? Is that also possible?
But the stabilization are old forms, right?
No, but what I'm saying is that one of them would have UP eigenvalue 1, one of the level raisins would have UP eigenvalue 1 and the other one would have UP eigenvalue P, for example. Is that not possible?
In this case, UP eigenvalue 1 and the other UP eigenvalue P.
Because I saw just in your paper, you specifically constructed a TP Hecke eigensystem where the UP eigenvalue was 1. And that just got me kind of confused because for some reason it's always congruent. This raised Hecke eigensystem that you construct is always congruent has always UP eigenvalue 1 or
that's true.
F1, which I just didn't understand the whole situation with respect to this, I guess.
I guess you're right. I guess the unique, the one that's the lift that happens on this Shimura curve or the character group or the component group is a particular one that has UP eigenvalue 1. Yeah. I think the reason you pick a particular one is the way you construct this. Yeah, you're right. Construct this congruences.
So is there I guess the thing I really want to ask is are there no others? Is there a reason there can't be one with UP eigenvalue P modulo L to the n, or is that also possible?
That's certainly interesting. I'm not sure.
Okay, no problem. Yeah, I was quite confused about this, so I'm just wondering.
Yeah, but I feel this just has something to do with the Tate twist. Yeah, but I'm not seeing this correct at the moment.
Okay. Yeah, no worries. And if it's not too much bother, I just have one more tiny question.
Yeah, no problem.
I'm just curious, where exactly, following some of your computations, I sort of saw in the calculations, the intersection matrix having rank 1, for example, why it was important that L doesn't divide P plus 1. But the assumption is that L doesn't divide P squared minus 1. And I can't quite figure out where the fact that L doesn't divide P minus 1 is actually used in the proof, just in a technical level. Can you point to it maybe?
Yeah, because I did the computation first. Not sure. I first did do the computation at QP squared, right?
Right.
And here you don't want your, so the eigenvalue is epsilon and epsilon p, right? Mm-hmm. But over QP squared, there is no distinct, it's just 1 and p squared, right?
Yeah, like
and I want to want p squared equal to 1.
Yeah, I guess why, like what exactly goes wrong if the eigenvalues, the Hecke eigenvalues are the same? That's what I'm confused about, I guess.
I guess this has something to do with
maybe.
Because yeah, the thing I was talking about earlier, like oh no, never mind. Sorry.
So maybe we will just thank the speaker again, and then we can postpone the discussion another time.
Oh, okay.